We look at these two elements as neutral elements, looking at where they are on the periodic table. The cesium should have one valence electron, and it only has one electron in the 6s. So if we were to write its electron configuration, it would be xenon and then a 6s1. So that one dot's just representing its one valence electron. For the selenium, if we write its electron configuration, start from its core, which would be argon. Then outside of argon, it has 4s2, 3d10, and then 4p4. So how many valence electrons does selenium have? 6. It's got these two and these 4, right? Again, the third energy level is not the valence level. If there's electrons in the fourth energy level, then that's the valence level. So I've got 6 dots to put around here. So this is how you would show if the element were neutral. The quiz question, though, said that you want to make an ionic compound, or that you have ions of these substances. And that the reason for that is because in nature, metals almost always already exist as ions. It's very rare that you find a metal, unless it were maybe gold or platinum or one of the metals that's really stable as a neutral atom. It's very rare that you would find a metal as a neutral atom in nature. So what I could tell by some of your quiz answers was that you're using the strategy of, okay, I'm going to put these two together. So if I start this neutral and I start this neutral and they come together, then I could imagine the electron moving from the cesium to the selenium, and then I would need another cesium with its electron to move over here as well. So that's fine. I mean, you can do that on paper. The only problem with that is that's not how the elements actually behave. There is no cesium neutral metal in nature. You can't, if you're going to mine cesium metal, it doesn't come out of the ground with a valence electron because it's not stable. Right? So in nature, you have to remember that there's atoms all over of all the different elements. And so since the metals, what they have in common is loosely held outer electrons, because especially with cesium, when it loses that electron, it'll make a noble gas configuration. It's already lost that electron in nature. It doesn't have that electron, so it's not really correct to say that the cesium will bring its electron and transfer that electron to selenium. And I know a lot of textbooks and programs will teach an ionic bond as a result of a transfer of electrons. But in nature, that's not really what's happening. It's not like you have these together, they come together, and they transfer the electrons from one to the other. They already have adjusted their number of electrons. Cesium already exists with a +2 charge. I'm sorry, a +1 charge. It already has that electron gone. So a better way to think about this that actually is more representative of how these elements actually behave is if you start with the element on the periodic table, assuming that it's neutral, and you realize, okay, this isn't how the element actually exists because it's more stable with the noble gas configuration, what you want to do is to say, how will it actually exist? What will its charge be if it makes a noble gas configuration? So a couple people did that, a couple groups did that. You realize that cesium needs to lose that electron, and when it does, it'll be a plus. And selenium needs 2 electrons. If selenium's a nonmetal, which it is, it should be able to get those electrons from other stuff in nature. It should already exist naturally with a -2 charge as a result of already having picked up those electrons. So when cesium and selenium come together to make a bond, they already have the charges. They don't have to transfer electrons. An ionic bond does not require electrons to be transferred because the charges already exist in nature. What happens here to make the ionic bond is simply an attraction between opposite charges. which we already know opposite charges attract. It's like the most fundamental thing about chemistry that allows us to explain almost everything we've been working with. So if the cesium has an overall plus and the selenium has an overall 2 minus, those opposite charges will attract and they'll stick together. If I want to make a compound that combines these two elements, though, it must be neutral overall. So the reason I know that there should be 2 CS for every 1 SE is because of this. Right? If I make a compound and I'm buying that from the chemical company, or I'm mining it out of the ground, or I'm dealing with a little bit of the sample in my lab, even just a pinch of this compound is going to have billions and billions of the atoms. So if I have a unit that represents this combination of cesium and selenium, and I have billions and billions of those units over and over and over again repeating to make up enough material to see with my eyes, each unit has to be neutral overall. Right? So if I combine cesium and selenium with a +1 and a 2 minus, and I combine them into 1-to-1 ratio, and I have an extra overall net -1 charge on every unit, and then I try to put that unit next to other units that also have a net -1, they're never going to stick together. So I can't make a material with a net overall charge on each individual unit that makes up that material. So there has to be a net 0 charge. That is how I know that I need 2 cesiums for every 1 selenium to make the charge balance. That's the logic that I use, the full and complete explanation for why the ratio is CS2 SE. Because each unit to be neutral requires 2 of the positive charge units to balance out the 2 negative charges on 1 of the SE units. So once you determine what the charges are, there's a kind of a quick way to determine this. You can take the quantity of charge for one and let it be the subscript for the other, and take this quantity of charge and let it be the subscript here, so you get 2 and a 1. Or you can just recognize if I already have more negative charge and less positive charge, I need more of the positive charge. So just increase the amount of positive charge until they equal out. But the first thing you want to do is determine what will the charges be in nature already. And that doesn't require them to start as neutral elements, meet up, and then exchange electrons usually. What we'll see as we go through here, just to illustrate another example, is that sometimes atoms will join together and share electrons, and that will have an overall charge. So you may have a polyatomic ion, something like this. We're not going to talk about this too much today. We'll probably talk about it a little bit more later, but just wanted to point out how I could give you an example like this. If I give you a polyatomic ion with an overall charge, that means that the sulfur and the oxygen are sharing electrons. Overall, this unit has a -2 charge. Right? So if I say I want you to join sulfate ions with ions made from sodium, actually let me just go with aluminum. You can't really use the method that you may have used on the quiz, which would be to maybe transfer electrons from one to the other and figure out how many electrons need to be transferred, because the SO4 doesn't need to gain or lose any electrons. It already has the electrons it needs to make a noble gas configuration for both the sulfur and the oxygen in that arrangement of those atoms. So if I think about the aluminum being in 3A and having 3 electrons, 2 are in the 3s, 1 in the 3p, so 3 total valence electrons. I'm not going to think about transferring these electrons to the other thing. I don't need to think about that because I know if it's a metal, it should already exist in nature. When you mine aluminum ore or bauxite out of the ground, the aluminum already has a 3+ charge. The aluminum already exists having lost those electrons and giving you a noble gas configuration that's the same as neon. So if I'm trying to make a compound that combines these ions and these ions, I have to first figure out what will the charges be on each of the individual ions. And so this combination of sulfur and oxygen has a -2, and the aluminum has a +3. So if I join them together and make a compound, I need to make sure that the aluminum and the SO4, that I have enough of each so that the overall charge is balanced out. So how many of each do I need? Well, I can take the exponent of one and make it the subscript for the other. It's kind of a shortcut way to do it. But if you want to make sure that that makes sense to you, another way to do it is to say, well, the aluminum already has more charge than the SO4. So if I have more positive than negative, I need more negative. So I'll bring in another SO4. Now I've got 4 negatives and only 3 positives, so I need more positives. So I'll bring in another aluminum. But now I've got 6 positives and only 4 negatives, so I'll bring in more negative. So now I've got 6 negatives and 6 positives. That's when it's balanced. So that tells me why I need 2 aluminums and 3 of the SO4 units. Questions about that? Okay, cool. So when you're operating with individual atoms, so this chapter starts with the individual atoms because the polyatomic ions are more complicated. But when you're operating with individual atoms, you can start with a neutral electron configuration, but you want to still recognize that metals are not going to be stable if they don't have a noble gas configuration. There are lots of exceptions to that. So when I'm saying that, what I'm referring to mostly are the first 2 columns. Group 1A and 2A metals will pretty much always be found with either a +1 charge on the group 1A metals to make the same number of electrons as a noble gas, or a +2. So if you want to know what will the charge be on this element in nature, adjust its electrons so it has the same number as a noble gas, and then if you put extra electrons in, that means you're putting extra negative in. If you had to take electrons out, you're taking it negative out, so now you have an imbalance and there's a net extra positive. So for sodium, that's what you would do. You want to figure out how it's going to be stable in nature, how it's going to exist. It's got to have a noble gas configuration. So this is its noble gas configuration. So it has to lose that 1 electron in the 3s. And when it loses 1 electron, it won't have a total 11 positives and 11 negatives anymore. Now it has 11 positives and 10 negatives. So the net charge is shown with a plus next to the element as a superscript. Right, so you would have, on the quiz, you would have wanted to do that for the cesium to show that's how it has a positive charge. Then, if your element is on the other side of the periodic table and it's close to a noble gas and it needs to gain electrons to make the same number, you do the same thing. Say, okay, what noble gas is next to chlorine? It'd be argon. So argon has a 1s2, 2s2, 2p6, 3s2, 3p6. So the chlorine really needs to just gain 1 electron. So if I give it that 1 electron, now instead of having 17 protons and 17 electrons, now it has 17 protons and 18 electrons. So there's a net -1. So the charge that's shown as a superscript to the right of the element is the net overall charge, considering how many protons there are and how many electrons there are and whether or not they balance out. So when you go and you get salt from the ocean or whatever, salt mines, you're not pulling out of the ground sodium and chlorine and then bringing them together and allowing electrons to be transferred from the sodium to the chlorine. They already exist as ions. What you're pulling out of the ground is sodium chloride, the salt. You're pulling out a combination of ions that stick together because they're oppositely charged. What holds an ionic bond together? The fact that positives and negatives attract. Any two atoms that have a net charge, if they're opposite charges, they'll stick together. You can make an ionic compound from that. That's what the ionic bond is. The ionic bond does not require electrons to be transferred. It's only opposite charges that happen to be able to get close together, and the attraction pulls them in. So let's just do a couple electron configurations. I might ask you a question like this. Let's do the barium 2+. So for barium, it has 56 electrons. So I don't want to go all the way back to the beginning, so maybe I'll just start with Kr. After Kr, I've got 5s2. Then I've got 4d10. Then I've got 5p6. And that gets me to xenon. And then I have two more beyond that. And so that's the 6s2. So ultimately I realized this is also a noble gas. So that is xenon. And so the nearest noble gas to barium is xenon. And so really what it needs to do is lose these two electrons. And I already know that. I don't really even need to know that barium is +2 is what I'm working toward. If I just tell you, make an ion from barium, and I don't even tell you whether it's going to be a positive ion or a negative ion, you can determine that because you recognize that it's got these two extra electrons, and it really wants to get to a noble gas configuration. So if it loses these two, it will have a Kr. Well, really, it will just be Xe, but you could write Kr 5s2, 4d10, 5p6. And so that's a barium 2+. So a barium 2+ has the same number of electrons as xenon. That's what makes it stable. That's why barium exists as a 2+ naturally. With the nitrogen's 1s2, 2s2, 2p3. The nearest noble gas for it is neon. And so neon, for nitrogen, to get to neon, it needs to pick up 3 electrons. That's why it has a -3, naturally. So if I pick up 3 electrons, I get 1s2, 2s2, 2p6. And so that's for a nitrogen with a 3-. I don't care if you do nitrogen 3- or nitrogen -3. Either way, it's the same thing. I don't care. Okay, so let's look at some D-block elements because they're a little different from what you might expect, and then we'll take a break. So the D-block elements, we would approach the same way. So the tricky thing about the D-block elements is that they are, most of them at least, are too far away from a noble gas to make a noble gas configuration. So if we look at, say, iron, in order to make the same number as a noble gas, iron would have to pick up 10 electrons or would have to lose 8 electrons. That's too much. Right? So an element will often gain 1 or 2, sometimes 3, or sometimes it might lose 1, 2, 3, maybe 4 max. But once you go beyond losing or gaining 3 or 4 electrons, you're creating a very imbalanced charge on the atom. And so if I have an atom and I keep taking electrons out, so like for iron, I take 1 out to make the same number as manganese, take 1 more, keep taking electrons out to try to get to the same number as a noble gas. As we saw with ionization energy, every time I remove an electron, the remaining electrons have a little bit less shielding. So if I keep removing electrons, and there's less and less shielding between the remaining electrons spreading them out, they just get closer and closer to the nucleus and held more and more tightly. The effective nuclear charge increases every time I pull an electron out. It's harder to keep pulling them out. So eventually, if I try to keep pulling electrons out, I can't. The remaining electrons are held too tightly. So for a lot of these D-block elements and the F-block elements, they're not going to make a noble gas configuration. So how can you predict what their charge will be? You can't. And in fact, some of the elements exist naturally with different charges. So iron exists in nature with a +3 sometimes with a +2. So if I just say, here's an iron atom, what should its charge be? You can't answer that. Which is nice, because then you don't have to worry about answering that. But you should be able to give the electron configuration if I give you the iron. So if I tell you it has a +2, that particular iron atom, its electron configuration, you would find it the same way. You would start with the neutral iron, and then you would take out the valence electrons, which for iron are not the d electrons, they're the s electrons. So this is energy level 4. This is the valence level. It's the highest level, highest energy, principal energy level with the greatest quantum number. So it's the valence level. N equals 4 is greater than n equals 3. Those are the electrons I removed. So an Fe2 plus has this electron configuration. How many valence electrons does an Fe2 plus have? First of all, how many valence electrons does an Fe have? Two. The fourth level is the valence level. There's 2 electrons in that level. If I remove those 2 electrons, now the fourth level is not the valence level anymore because there's no electrons in it. The highest level that actually has electrons now is level 3. How many total electrons are in level 3 now? Well, let me write the whole thing. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. 14. If the fourth level doesn't have any electrons, then all of the third level is the valence level. So I've got 14 valence electrons. Iron also exists often with a 3 plus. So if I'm looking at a 3 plus iron, I would do it the same way. I would start with the neutral iron. Even though I know the neutral iron doesn't exist naturally, I can find what form of iron actually exists naturally by starting with the neutral iron and adjusting the electrons to give me the charge that I know the iron should have when that's given. So if I know it should have a 3 plus, I need to take out 3 electrons. So first, just with the other one, I take out the valence electrons, remove the valence electrons first. Once I don't have any more electrons in the fourth energy level, now the third energy level is my valence level. So I would take 1, so I'll lose 2 of those, and I lose 1 of the 6 electrons in the 3D, because that's the highest subshell in the what now is the third level, which is now the valence level. So now I only have 5 in the 3D. And so I have a total of 13 in the third energy level now. So 13 valence electrons. This is also nice because I have 5 out of 10 filled in the D subshell. That's exactly half full. So that's why actually the iron 3 plus is more common naturally than the iron 2 plus. You might say, well, once I remove these 2 and make iron 2 plus, since I remove 2 electrons, I have a little bit less shielding. To remove this extra electron, it should take a lot of energy. It should be difficult to do. But it's not as difficult as you would expect, because when I remove these 2, and then also that 6th electron in the 3D, I make an exactly half-filled subshell, which is a little bit extra stable because of that exactly half-filled subshell. So that's the way iron exists most of the time with a +3, but sometimes also with a +2. Any questions about that? All right, let's just do one example, then we'll take a break. So I'll just pick one of these. So I'll just look at the chromium 3+. So chromium close to iron, so I would start with the argon core. Then I've got a 4s2. And then chromium's the fourth element over. So then I have a 3d4. Is that the correct electron configuration for a neutral chromium? No. Chromium was one of the exceptions we learned for the neutral atoms. The correct electron configuration for chromium actually already shifts one of the 4s electrons into the 3d to give it an exactly half-filled subshell. If I want to now make this neutral chromium into a chromium 3+, I just have to take away 3 negative charges so that there's a net overall positive. So first, I remove the valence electron. Then I would remove 2 of the third energy level electrons, which would become the valence electrons after I remove the fourth energy level electron. So I would get argon 3d3. That would be the electron configuration for a chromium 3+. So why does chromium do that? I mean, once this electron's gone from the 4s, it has a half-filled 3d subshell. So why doesn't it exist with the chromium plus? Chromium plus 1 would have argon 3d5. That would be a half-filled subshell. It lost that fourth energy level. Why would it continue to lose more electrons and go to a +3? Well, that's a difficult question to answer if you just think about chromium in a vacuum. If I just think about having one chromium atom and there's nothing else around it, and I'm just thinking about, the attraction the electrons have to the nucleus and getting the half-filled subshell or getting a noble gas configuration if it were a different element maybe, I have to remember that in nature there are lots of other elements around. All these elements are competing for electrons. Every element has some number of valence electrons. And the other elements nearby, they have a nucleus that could attract those valence electrons. So it's really just a competition. So that's what makes metals metals. They just don't hold on to their electrons as tightly as nonmetals. So since there's oxygen in the air, which is a nonmetal, there's halogens that exist in nature, over time, these elements that attract electrons better because they have a lot less shielding or they have more protons, they just pull the electrons out. So it's just a matter of the third energy electrons in chromium, because chromium doesn't have that many protons to hold 3 full energy levels in. It's just not good at holding all those electrons in compared to other elements that have less shielding and maybe can pull those electrons closer. So it's just a matter of competition. So the reason chromium exists with a +3 is just because there's so much shielding, it just can't hold very many of its d electrons in. And so they just get attracted to other elements better than the chromium attracts them in. So we can't always explain everything just based on trying to get a noble gas configuration or trying to get an exactly half-filled subshell.